students, welcome back to our course Environmental Modeling and Simulation. Today we are going to look at a model that shows bifurcation, saddle node bifurcation, and it is used to model the health of a forest. It is a continuation of the insect outbreak model that we studied many lectures ago, and I gave you a brief preview of this model and its various parameters in the previous lecture. So let's get started. We have ds by dt. S here is the forest cover. Basically tells us the cover of a particular kind of tree, the spruce fig tree, which is eaten by the spruce budworm, whose leaves are eaten by that budworm. So we are focusing on that tree, and the growth of this tree and its tree cover follows a logistic kind of growth model. So what we see is something like this. However, it is also associated with the capacity of the forest, which is E, which is limited by Ke. So we see that this is a product of two limiting functions, and then we have dE by dt, which is the health of the forest is determined by, again, another logistic looking model. However, the health of forest is adversely affected by the outbreak of insect or the prevalence of the budworm, which eats up the leaves. So we have a minus term which subtracts the health of the forest and is proportional to the budworm population. So very quickly, let's take a look at this model. Let's try to make sure that we understand all the parameters. There are many parameters, and we are going to non-dimensionalize the system soon. Rs is the growth rate of the tree cover, and this is when it is unimpeded by any kind of limitation of the health of the forest or limitation of resources. Ks tells me the limitation or the maximum amount of trees that a forest can support. Ke tells me the maximum health or the ability of a forest to support such trees. E is again representative of the health of the forest. Re is the rate at which the health of the forest increases. Ke is the maximum level it can reach. And then we have this term here which tells us about the detrimental effects of the budworm population. B is directly proportional to the budworm population. S, you should remember, is the tree cover. So the more the tree cover we have, the forest will have greater resilience in context of its health, in context of its energy, because S is big, then PB by S will become small. Okay, well, the first thing we are going to do is we are going to non-dimensionalize the system, and this one is going to be pretty easy. We know that Ks and Ke are the limiting terms for S and E, so we can define a new S. This is a small letter s, which is equal to capital letter S Ks. We can define a new E, which is capital E by Ke. So ds will be equal to, and dE will be equal to. Now we can substitute this in our equation, and what we'll get is so this is what happens to this equation, and now let's take a look at the second one. So we can simplify this. You notice in this equation we have Ks on the both sides. So this equation will become d small s by dt is equal to Rs s 1 minus s by E. So this looks pretty comfortable. Now here also we can take Ke common. So we are left with dE by dt is equal to Re 1 minus E by Pb Ke Ks and small s. Now it's time to non-dimensionalize our time. So we can take a hint from this particular equation, and we can bring Rs on the LHS. So we have ds Rs dt is equal to s 1 minus s by E. And now the new time that we are defining is Rs t is equal to tau. So Rs dt is equal to d tau. So this becomes very simply ds by d tau is equal to s 1 minus s by e. So this equation we have non-dimensionalized. Now let's put this value of t, this value of nu tau here, and what we'll get is we can take the Rs from LHS to the RHS. Okay, now individually each factor in this model, in the second equation, is also non-dimensionalized. We have to define non-dimensional parameters so that the whole equation is completely non-dimensionalized. So let's introduce a new rate factor. Let's call it R, which is equal to Re by Rs. Now let's take a moment and look at this. It is the rate at which the health of the forest increases to the rate at which the tree cover increases. And now let's define a new parameter, which is a small b, which is related to the budworm population. So this becomes small b. So our small b is equal to Pb by Keks and Rs. Let's take a look at the new b we have declared. It is proportional to the level of budworm population in the forest, inversely proportional to the maximum amount of health of the forest and the tree cover in the forest and the rate at which tree cover is changing. So now our new non-dimensional equation becomes Re 1 minus E minus B by S. And here we have this. So now we have two non-dimensionalized equations in our 2D system, and we are going to draw the null lines to figure out what this looks like. So this is our system, just to summarize. Now, one of the first things I'll encourage you to do is to draw null line. So let's figure out S null line. So S null line is when ds by d tau becomes 0, which means S into 1 minus S by E becomes 0. So when S is not equal to 0, because if S is equal to 0, it means there are no spruce trees left. There's no food for budworm. So basically we reach a place of extinction. But here, when S is not equal to 0, then S is equal to E for this null line. Now let's look at E null line. For E null line, this situation should be met, which means so this will give us our E null line. So if we draw this equation, the S null line is very simple. We get a line like this. So this is our S null line when ds by d tau is 0. And then our E null line is very interesting, and it looks like this in the second quadrant. In the third quadrant looks like this. And in the first quadrant, where it is relevant because both S and E are positive, it looks like this. So what we notice is that when B is sufficiently large, this curve here moves to the right. And when B is sufficiently small, this curve moves to the left. So we notice that as B changes, it will either be this situation or a situation where this curve will intersect this line in two places. So depending upon the B value, we'll either, when we are talking about only the first quadrant for S and E to be both positive, we'll either have two fixed points or we'll have no fixed points. Now since as the value of B changes, the number of fixed points are changing, this is an example of saddle node bifurcation. Now what we want to do is we want to understand the behavior of the trajectories around these two fixed points when there is an intersection. So we notice that our graph looks like this. So now we have two fixed points for a sufficiently small value of b. What's telling us that when the birdworm population is sufficiently small, there are two possibilities for the forest to have. There are two fixed points, and now we have to understand the behavior of the trajectories around this fixed point. And the easiest way is the null cline method, which is what we are using now. So we need to remember first what the equations are. And the equations that we have are ds by d tau is equal to S1 minus S by E, and then dE by d tau, this is small alphabet s, okay, and we are varying b right now, we are not varying the other parameter r. So let's look at ds by d tau. So this S null cline is this one. So right now we are looking at this region. And in this region, let's first look at the S null cline because it is much simpler. So S null cline is basically S by E, E minus S. Now when we are in this yellow highlighted portion, the value of E is higher than it needs to be. In fact, even within this particular area of the curve, but we are going to leave it empty for now because we are going to look at it separately. We're going to look at one segment at a time in the first quadrant, and right now we're only looking at the yellow quadrant. So in this, not quadrant, segment. In this segment, E is higher than it needs to be for ds by d tau to be 0, which means that ds by d tau is going to be positive. So here we have ds by d tau is positive, it's more than 0. Now let's look at the value of dE by d tau. The null cline for dE by d tau. Now let's look at E null cline. So this is E null cline, and this is the equation equal to 0 is our equation for E null cline. Now here in the yellow highlighted portion, we are above the E null cline, which means the value of E is larger than it needs to be for a given S for that point to lie on the E null cline where dE by d tau is equal to 0. As E will increase, what will happen is that this will become negative because E null cline sort of becomes tangential to E is equal to 1. So what will happen is that dE by d tau will become negative. So here we have the rate at which E is changing with time is negative in the yellow highlighted portion. Now let's look at other segments that are made by these two intersecting null lines. So let's look at this gray area. Now here let's start with S null cline because it's the easiest. We are below the S null cline, so E is lower than what it needs to be for the point to lie on the S null cline. So when E is lower, ds by d tau is going to be negative. So now ds by d tau is negative, but dE by d tau is still also going to be negative. So both S and E are going to reduce in this general region. Now let's look at another segment. Now in this warm gray segment, we are below the S null cline. So I'm starting with S null cline because it's an easier null cline. It's just a straight line with starting from origin, and it's S is equal to E, so the slope is 1. Now in the warm gray region, it's below the S null cline, so we know that E value is less than what it needs to be, so we are expecting that ds by d tau will be negative. So here we have ds by d tau is negative, and the dE by d tau will be opposite, it will be positive. Now let's look at another region in this cool gray area. It's almost blue. Now this region is above the S null cline, which means ds by d tau is going to be positive. Now one thing I want to clarify, every time some area is above a given null cline, it does not mean that the variable corresponding to that null cline is going to increase. This is a particular situation here. How do you determine whether ds by d tau is going to be positive or negative? Will depend upon the function. So in this case, we have ds by d tau is equal to S by E, E minus S. Now we know that when E is equal to S, ds by deta is equal to 0. As E will increase, E minus S will become positive, which means since S by E is already positive, ds by deta will become positive. On the other hand, as E reduces, E minus S will become negative, which means ds by deta now will be a product of a positive factor and a negative factor. It will be negative. So this is how you need to look at each individual equation to understand the sign of ds by deta above or below a given null-cline. So here in the blue highlighted area, the cool gray highlighted area, the rate at which S is going to change is going to be positive. So ds by deta is positive. Now let's look at dE by deta. Since this is inside the E null-cline, this is going to be our scenario. Now let's look at the last region we have. I'm going to highlight it in greenish gray. Now this region is below the S null-cline. So ds by deta is going to be negative. Now dE by deta is very fascinating here, because for a given value of S, we have two values of E. Now outside this curve, we know that dE by deta is negative. So dE by deta here is going to be negative. Now it's time to put our arrows together and understand how the trajectories are behaving around these two intersection of null-cline points. So let's start with the yellow one. ds by deta is positive, dE by deta is negative. So in S direction there is increase, in E direction there is decrease. So the net flow is going to be in this direction. Now let's look at the gray area. ds by deta is negative, dE by deta is negative. So in S direction, this is S by the way, we are moving towards left side. In E direction we are moving towards downside. So net movement is going to be here. Now let's look at the warm gray, the reddish gray portion. ds by deta is negative, so the flow in S direction is on the left side, dE by deta is positive. So in this direction, net movement is going to be here. Now let's look at the green gray area, which is below the E null-cline. Here ds by deta is negative, dE by deta is negative, both are reducing, so the flow is going to be pointing like so. And now let's look at the blue gray area. ds by deta is positive, dE by deta is positive, so flow is going to be like this. Okay, now what we can do is we can put a picture together. It's very evident that the second fixed point is a stable fixed point. So now let's color this fixed point. If you remember, we are still following the same, what's the word? We're still following the same symbols, the same the practice of filling in the stable fixed point. So this looks like a stable fixed point. So let's make this a filled circle. Now let's look at the second circle. What we notice is that the flow around second circle will look like this, moving here. So there appears to be some unstable manifold in this direction and a stable manifold in this direction. So what this one appears to be is a saddle. Now of course we can find out the Jacobian, we can find out the values of the fixed points, and then we can find out the characteristic equation, eigenvalues, eigenvector, and figure out what exactly is the state of these 2 points. But this is in itself enough for us to understand what is happening here. In the positive quadrant, in the first quadrant where both S and E are positive, which is relevant for a forest system, there are two positions, two ultimate positions, one of which is stable, one of which it is a saddle. There are two positions for E and S value. One of them is stable, which means that if the trajectories are in the neighborhood of this particular fixed point, they will be attracted to it. And this is a value where E and S are limited, but they have a higher number than the lower value fixed point. The lower value fixed point is a saddle where the unstable manifold where the unstable manifold tends to point towards the stable one, which means that the stable manifold, which will be somewhere in this direction, now we can find the eigenvector and figure out the exact direction of this stable manifold. The stable manifold of the saddle point will determine whether the E and S value in the forest are pushed towards the stable fixed point or they are pushed down. Now remember, around the saddle the flow looks like this. We have a negative fixed point too, but we are not looking at it. Now if the initial values of E and S are above this stable manifold, then we know that our forest is going to find equilibrium here in the stable fixed point. If it is below, if the initial values of E and S are below this particular stable manifold, then both E and S are going to be reduced. They are going to go to extinction, which means the forest will die out. So we are already seeing that there is a particular stable manifold. Now we can find the position of the stable manifold. And this is happening only for certain values of B, when B is small enough. So when the spruce birdworm population is small enough, there is a stable manifold for a saddle point which is lower than the fixed point which is stable. So basically the forest wants to move towards stability. There is a good chance if you have sufficient E and S for the forest. Now what happens when the birdworm population increases? When B increases very rapidly, what we see is that the fixed points disappear. And remember, this is a saddle node bifurcation. So that's why the fixed points are disappearing. So what we see then, our phase portrait looks something like this. This is our S null cline. And this remains in positive quadrant, this remains our E null cline. And they are not intersecting. So now if we look at the flow around these two null clines, so if you look at this area that is above the S null cline, we are going to have some very similar flow behavior where ds by d tau is going to be positive, dE by d tau is going to be positive. And if you look at this area, ds by d tau is going to be negative, dE by d tau is also going to be negative. So the flow is in this direction. Here, made a mistake, dE by d tau is negative. So the flow is in this direction. In this region, which is the warm gray, reddish gray region, ds by d tau is going to be negative and dE by d tau is going to be positive. So we are going to have flow in this direction. So basically our flow lines will look like this. For a sufficiently large population of B, both the E and S are going to go towards 0. Remember, in this quadrant, we still have a fixed point. So they are all going to go towards 0. So we are going to lose our forest health, we are going to lose our tree cover just by varying the birdworm population, which is B here. Now you can also vary R and see how that affects in the whether it causes a bifurcation or not. But the bifurcation that is relevant here, the saddle node bifurcation, is dependent upon the parameter that represents the birdworm population. Alright students, this is all for today's lecture. In the next lecture, we will continue our examples of bifurcations in 2D systems and also explore hop bifurcation and the environmental scenarios where they are relevant. Thank you.